Okay, so as we said that chapter 5 are 4 with you, in some books maybe 3. There are different editions. I have online. I have the hard copy of the book, which is second edition. So they are a little bit different, but the content is not. The content is not much different. So the carrier transport phenomenon. So carrier transport means current, right? Charge carriers moving across a semiconductor sample or inside the semiconductor. So that will mean current. And to be precise, we should talk about the current density, right? Current is like resistance, and current density is like, resistivity, a more reliable current. So current density we should talk about, right? In a semiconductor sample or in a solid uh, sample, we will say that current should be like of two types, right? When there is an applied electric field, the free charge carriers, the charge carriers which are free, right, will feel some force, and that will give rise to a current. Current is the motion of charge carriers, we will say, right, due to the application of electric field. Another type of current should be, current is the flow of charge carriers across a point. So another type of current will be if the number of charge carrier at one point is greater than the number of charge carriers at another, then they will try to keep into to bring equilibrium, right? So the electrons are the charges from high concentration area, they would move to low concentration area. So this will again give rise to a motion of charges. So current. So these kind of two types of currents. The current due to applied electric field, we call it drift current. And if we represent it by current, or we say the current density, usually it is represented by J. So there is one type of current, we call it drift current, the current due to electric field. And I will represent it JDR, the current density because of the electric field. The other current, right, which should be because of the concentration gradient, right? The concentration of electrons or charge carriers is different at the 2 points inside the sample. Here, for example, it's greater, and here, for example, the concentration is smaller. So there is a concentration gradient. And due to this concentration gradient, the charge carriers or charges will move from high concentration point to lower concentration point. This will give rise to current. This current is usually named as diffusion current. Right? I should represent it by JTI, diffusion current. Right? So two types of current inside a semiconductor sample we can discuss. Right? Now, let us discuss the situation of drift current, right? Drift current density. Drift current density. right? So let us talk about the situation when there is an electric field present and charges move in response to the application of the electric field. Okay, so we can write current density or the drift current density is equal to rho, right? Suppose we are talking, there could be like current due to holes or current due to positive charges or current due to negative charges. So usually we prefer current due to positive charges because we take it positive and it has been a convention. So we talk about the current due to holes. Suppose we have holes there and suppose that is the density of holes. Rho P is the density of holes and V dP is the drift velocity. dP is the drift velocity, right? The current is proportional to what? The speed of force, right? And if the density is constant, right? So that is rho dP. So J, the drift current is proportional to the speed, right? If rho P is constant, where rho is the density concentration of holes, right? The density of holes. Okay. Now, this rho P, the hole density, right, is like E and P. So here, P is equal to concentration of holes, right? So that is the density of charges now. The density of charges and the speed, and this gives rise to that is the definition of current density. Right? So now we can write current is the charge density is the charge of electron multiplied by the number density of holes. Right? Or we can write this as G the drift current can be written as equal to E P holes and VTP, right? Where VTP is, as we said, that is the velocity or the speed of the drift velocity of holes. By drift velocity, we mean an aggregate velocity. Right? There will be many particles, right? And they all will be moving in the form of a group. So that drift velocity is the velocity, the average velocity of the whole group. That is the average velocity of the group. For example, I will just give you a simple example. जिस तरह आपके पास भेड़ बकरियों का एक वो होता है रेवड़ होता है, right? So when that moves, कुछ बकरियां might be moving in the opposite direction, एक दूसरे के साथ लड़ते होंगे कुछ, लेकिन इनकी अपनी एक एवरेज वेलोसिटी है, right? जो है वो average velocity body. That velocity is called the drift velocity. Some particles might be moving. That's the group velocity. The velocity of a group of electrons. Some electrons might be individually at a certain time, might be even moving in the opposite direction to the group velocity. But that does not matter. So that is the drift current, right? Now, there is another phenomena which is very important in semiconductors and which we usually talk about students talk about in research about that property. And that is called mobility. Mobility of charge carriers, mobility of holes, or mobility of electrons. right? So here we talk about mobility, right? We said that the current density, right? The current density here is proportional to the velocity of force, the drift velocity of force. But the velocity in itself is responded to some other thing, and that other thing is field. So the velocity is a response of charge carriers to the electric field. We can say that the velocity, the dp of holes, that velocity is proportional to the electric field. And greater is the electric field, usually we will say greater is the velocity, right? So we can remove this proportionality with introducing a constant, right? So VdP is equal to mobility mu and E, right? This constant which we introduced in this equation number 4, right? This is called mobility of the charge carriers, and this is a property of the semiconductor cycle. That is the property of the material. If you know the mobility of a material, you can know what is the nature of the what is that material. So it is kind of a signature property, right? So this is called mobility. And since the particles are holes, so we will put a little p, small p here, right, to signify that here we have holes here. So mu p is equal to mobility of holes. We will say, right, that mobility of holes can be written as V over E. Right, the mobility of holes is equal to. So mobility is actually the ratio of velocity. That is not potential. This is not potential. It is velocity. When we write it like that. So the ratio of the velocity of charge carriers to the electric field applied, that ratio is called mobility of those charge carriers. Greater is, we will see that greater is the mobility, greater is the speed of charge carriers in that particular semiconductor, and greater is the speed of charge carrier in that particular semiconductor, right? Greater will be the current density, the drift current density, right? So here, let us put equation number. Let us put equation number 4 here, and equation number 3. So equation 3 actually, equation 3 gives you, right, what? Equation 3 gives you J, the drift current, that is equal to E VdP. For VdP, we write this thing, mu P into P. So that is a form of the current density in which, right, there is electric field, there is mu P, which is the mobility of holes, and it is a constant. And that is P here is the concentration of holes. What are, how many holes are there? And then is the charge of each hole, the charge of electron, which is equal to the charge of a hole, right? So, That is the drift current in the form of the drift current in the form of electric field and mobility and concentration of force. Now, similarly, we can do it for electrons. This was for who, right? So for electrons, we can do it. And VTN for electrons, right? We can say that G D R. Your book right here is an extra N here, but I will put a prime over here. I will put a prime over. That is for electron. That is equal to, again, it will be equal to minus mu n, where mu n is the mobility of, oh, look, electrons. In the case of electrons, when you apply electric field, the electrons actually move opposite to the electric field. The holes, they're present there, they move in the direction of the electric field. But electrons, they move opposite to the direction of the electric field. Then we can write this equation for electron like this. Like the current density, we can look for electrons, right? So J, dr prime can be written as like as before, right? Minus E, the charge of electron is minus E. If we put the charge of electron as E, then that is minus E. M is the concentration of electrons, and V, right? The velocity of electrons, right? Now, we can say that here, the V drift, right, of electrons, that is equal to mu n and to E. We will say mu n is equal to mobility of electrons. Mobility of electrons, right? So the speed of electron will be opposite to the electric field. So we can write a negative sign here, right? Okay, if we put this here, I will write a prime here. If I put this here, we get the drift current because of the electron is equal to minus minus will cancel out E mu n, right, into E, right? So there is n mu into E, right? So that is the current density. Okay, equation 6 gives you the current density because of holes, right? Where there is a property on which the current density, the drift current density depends, is called the hole mobility. Here, it is exactly the same as this one, right? The only difference is that here we have the electron concentration and then electron mobility, right? So we can say that the total current density, right? Now, what is the total current density? The total J, right? So we can say J JDR plus JDR prime. Remember, I have slightly different notations from your book, right? So you should listen that I am using different sometimes different symbols. So the total current is equal to, that will be the sum of the current of electrons due to electrons and due to holes. We will add the two currents and that will be the total current density. Right? So put equation number 6 and equation number 7 here. Right? So what we get, that is equal to this current because of holes E, P and mu P and E plus E and mu n into E, right? So there are, like E is here, we can take E common. Similarly, E here. So we can write this is E, right? P mu P plus N mu N into E, right? That is the total current density, the drift current, total current density, the drift current density, right? So, that is the total current density because of the electric field. We can, approximate that how much, we can estimate how much is the amount of current density, right, at a particular applied electric field. The current density as a response to the electric field. We have a sample. The sample will have either N doped, or P doped, or both doped, and it will have its own mobility for electrons, and it will have its own mobility for holes. So according to this equation, it gives us the current density, the total current density, because of holes, because of electrons, and because of a certain electric field that is applied to. Let us do an example and just know what is the typical amount of current that flows in a semiconductor sample. Let us do an example, right? So we have an example. Suppose the sample is gallium arsenide. Right? That is the sample, right? Calculate J drift, right? And suppose the temperature is room temperature, which is T equal to 300 Kelvin, right? And suppose the applied electric field, right, that is 10 volts per centimeter. 10 volt per centimeter, right? Now, it is said that it is N-type doping, right? So the concentration of dopant atoms or ions Nd is equal to 16 10 to the power 60 per centimeter cube. That is the typical density of doped impurities in a semiconductor sample, 10 to the power, about 10 to the power 16 per centimeter cube. Right? So that is that. And Na is equal to 0. Suppose there are no accepted impurities, right? There we have only here dirt impurities here only. And from previous situation, right? We will need in the previous formula, right? We were calculating N, right? So for that we need Ni. So Ni at this temperature from our previous measurement, right? It is temperature per room temperature पे how many generally in gallium arsenide में how many atoms ionized हो जाते हैं? How many atoms get ionized at this temperature, right? That is from our previous knowledge of previous articles 1.8 and 10 to the 6, right, per centimeter cube. Remember one thing. Look, this is a very huge number, 10 to the power 16. And that is very, very small as compared to this. ये जो है, ये billion से भी ज़्यादा. This is more than billion. And kind of the order of a billion. Right? So this is generally the thermally ionized charge carriers are the charge carriers that we get in a semiconductor because of thermal excitation. That is very, very small as compared with the typical doping that is carried out in a semiconductor, right? It's not double, triple, it's like billions times greater, not more than billions times greater, right? So if we want to find, in your mobility, sorry, in your current density equation, that was probably our last equation, equation 7. The current density, J drift, was equal to E multiplied by N mu N plus P mu P multiplied by E. So we need N and we need P, right? A is, Na is equal to 0, so we will say there will be no impurity holes. The only holes present will be because of thermal excitation. And since thermal excitation does not produce a very large number of holes, it only produces, like, for example, at room temperature, it produces only kind of a billion of charge carriers. So the P and N are the same when they are produced due to temperature, due to heat, right? So let us recall the formula. We are going to find this thing, right? So J drift was equal to E and to me plus Q mu P and to E. Now we have to find out this thing, right? right? So for N, we know from our previous compensated semiconductors, for the formula for compensated semiconductors, right? So we know from there that N is equal to ND minus NA divided by 2 and plus ND minus NA divided by 2 whole square plus Ni square, where Ni is the number of electrons, intrinsic electrons, right? The electrons that are produced only due to thermal vibrations, thermal excitation, right? So that was the formula. Now we said that Na is 0. So we can remove Na. Also, this Ni square is very, very small as compared with this. So that will also go, that will be 0. This will go out of the equation. Right? So what we get will be like Nd divided by 2 plus here Nd divided by 2. Right? Which is equal to Nd. Right? So the number of total number of electrons present in this semiconductor at T is equal to 300 Kelvin. That will be equal to N is equal to which we here and to the power 60 per centimeter cube. So now we can find the current density because we said there will be no holes, or the holes excited because of heat energy that will be very, very small, right? So Ni means N naught and P naught. They both will go to 0 because they are very small as compared with N. So in this formula, we will say, okay, this term goes to 0. So what we have is J that will be equal to E, right, and mu n and to E over here, right? So putting these values here, the charge of electrons, n from here, mu n, the mobility of electrons in gallium arsenide. Right, let me write it here. The mobility of N, that is 8,500, and both are electric field. So what is that? So J drift will be equal to this thing, this thing, this thing, and this thing, and you get what? 136 ampere per centimeter square. And we find out like what should be we can find this like from both or electric field the units. I'm looking for the units of, but that will take time. So what is the, you can find it, what is the centimeter square per volt per second? Centimeter square per volt per second. That is the unit of mobility. Right? So the drift current is very, very high. This is a very high current, right? Very, very high current because of the applied electric field when semiconductors are doped, right? A very high very high current. So it means semiconductors become very, very good conductors when they are doped with impurities. Yeah, right? So impurities are good for semiconductors, right? It means that impurities are good for semiconductor. आमतौर पर impurities जो है चीजों की खालिसनेस को खत्म कर देती है ना, मिलावट इसको कहते हैं, मिलावट, राइट? दूध में मिलावट होती है तो अपने हुकूमत वाले आके इसको जो है वो करते हैं, चेक करते हैं, और सारे दूध जो है हम खबरों में और अखबार में देखते हैं कि सारे दूध को नालियों में बहा देते हैं, इसलिए कि वो कहते हैं इसमें इम्प्योरिटीज हैं, मिलावट होती है। लेकिन इम्प्योरिटीज हमारे लिए इज अ वेरी गुड थिंग, right? It's a very good thing. Impurity is a very good thing in semiconductors. It makes a semiconductor like a conductor and gives us a very high current density. 136 ampere per centimeter square is a very high current. Okay, so now let us go further, a little further. You know, in today's discussion, we got a very, we got to know a very interesting new parameter. And that new parameter, आज के लेक्चर में एक नए पैरामीटर हमने देखी, एक नई चीज का नाम सुना, and that is mobility. So let us explore more about mobility. ये तो कुछ नई चीज है, interesting है, and let us explore it further, right? So your book on mobility effects. Our mobility to our journey, right? Let us. I will say mobility now. How mobility changes with different things. Mobility किन चीजों पे डिपेंड करती है? On what does mobility depend? Right? Factors on which mobility depends. Factors on which mobility depends. Factors on which, let us find out this new parameter. Okay. Now we know that the force on a charge carrier, right? That the motion of the charge carrier will be obeying F is equal to ma, second law of Newton, right? At the same time, by definition, the force on a charge carrier is equal to the electric field multiplied by the charge, right? That is the force. So, as we said, I will follow the second law. Suppose it follows the second law. Where is the second law of motion? So we will say it is m f is ma. So m dv by dt, dv by dt, right? We can say here it's called Cp, mcd, effective mass of holes, conductivity effective mass of holes, right? The here in the semiconductor samples, the mass of an electron or the mass of a hole is not like a free, the mass of a free electron or a free hole. So the mass of a hole or an electron, we call it effective mass. The new name, effective mass, right? Which is the mass of that charge carrier inside a particular semiconductor, right? So that will be equal to E at the testing, right? That is equation number 1, right? Now, if we integrate this equation, right? With the constant of proportionality, constant of, not constant of integration is equal to 0, then we get V is equal to right E T and divided by the conductivity effective mass. The effective mass of holes. Look, the velocity of the charge carrier. The velocity of the charge carrier depends on the electric field, and it also increases with time. Because it should increase with time, because there is a force on it, and force produces acceleration, and acceleration will constantly change the speed of the particles, charge carriers, right? So it should increase with time, but the electrons are holes. They are not all alone. They are moving in a sea. So there will be hurdles to the motion. There will be hurdles to the motion. There will be collisions, right? So the velocity of electrons or holes cannot increase indefinitely. It will start increasing, go to a certain point, and then there might be a collision, and the collision will change the velocity. After you stop, you can stop the charge carrier, right? So the velocity, we can say that the velocity will increase for a time we can call some time constant, right? The time that is the average time between two collisions, right? So if T is the mean collision time, right? Then we will be equal to E, right? And I will write here the hole's mean time, the average collision time, because that will not increase from there. And the effective mass. Holes. There are so many indices like C and P and conductivity effective mass. So, but we don't have any other option because there are so many parameters, so many masses, so many T's, and so many variables that we have to use many subscripts and superscripts. Okay. So suppose that is equation number 3, right? Now we know that we can write this V by E, right? And that is E and tau dP divided by M dP into tau, right? And what is this thing? As we said, that was the mobility, right? So the mobility of holes will be equal to E dP divided by M dP star, the effective mass. right? This is equation number 4, suppose. Right? So the mobility here is a function of the average time of collision, as well as it is a function of the conductivity effective mass. Greater is the conductivity effective mass, smaller will be the mobility. And greater is the time between collisions, between two collisions. Greater will be mobility. Collisions ज़्यादा नहीं होंगी तो mobility ज़्यादा, right? So that is the mobility of holes, and similarly the mobility of electrons can be like E, C, C, and C and dot. Okay, so here the conductivity effective mass of electrons and semiconductors that is greater than, this is in from experiments, right? That is the effective mass and Cn of electrons. Electrons की effective mass जो है that is smaller than the whole effective mass. Whole effective mass से electron की effective mass कम है. So electron effective mass is small. So this implies that what is the consequences of this change in a difference in the effective mass? That mu n, right? The whole the electron mobility is greater than the whole. So we should keep in mind electron mobility is greater than the mobility of holes. Right? Okay. Collision is responsible for defining the mobility of a charge carrier in a semiconductor sample, right? If collisions are frequent, mobility will be smaller. If collisions are infrequent, mobility will be large, like greater mobility. So the collision can be because of situations. Like either there is a high temperature, the sample is at a high temperature, and the ions are vibrating like this, right? And in quantum mechanical terms, we say that those vibrations are producing phonons, quantum mechanical particles, which are related with vibrational waves or sound waves, right? We call them phonons. So the collision can be of electron or hole, or if we're talking about hole. So the collision can be with collision of holes with a phonon, a lattice vibration. Or the collision can be the electron might have a collision with an impurity atom. An impurity atom is, suppose it is an interstitial impurity. So it will be in the middle of somewhere, right? So it can either collide with a phonon, which is an like hypothetical particle, no reality. So a quantum mechanical concept. Or the holes can collide with an impurity ion. Right? So there are different mechanisms. So different mechanism on which mobility depends. I would say resultant mobility, right? In the case of multiple mechanisms, right? Yeah, different mechanism, collision, different types of collision, right? So suppose we say mu L is the mobility changes because of latest vibrations, because of collision with phonon. Huh? Collision with phonons. Collision with phonons, right? So from first order scattering theory, right, it is given that the mobility, lattice mobility, right, or the mobility that is influenced by collision with phonons or the presence of phonons, that is proportional to t to the power minus 3 by 2. Or you can say that mu L is proportional to 1 over t to the power 3 by 2. Greater is the temperature, greater is the temperature, smaller will be the mobility. Smaller is the temperature, greater will be the mobility. So the presence of phonons is inversely proportional to mobility, right? More are phonons, or more is the temperature, smaller will be the mobility, right? Okay. So what is the, like, collision is a statistical phenomenon. So what is the probability of a collision? How many collisions are there? So to find the probability of collision, right, we will say that in how much time. आप अगर मुझसे probability के मुतालिक collision के मुतालिक पूछेंगे तो मैं कहूँगा अतः कितने टाइम में, because collision is time dependent. बहुत ज्यादा टाइम पे बहुत ज्यादा collision होगी, स्मॉल टाइम में कम होगी. So if dt आप मुझसे कहेंगे अच्छा जी बताएं dt स्मॉल टाइम dt में कितनी probability है collision की, right? So I will say the probability of collision, right? L means latest vibration. PL, the probability, right, of collision due to latest vibrations. That would be equal to dt divided by tau. That mean time, right? That is the mean time between a collision. So that is kind of the total number of events, and that is the number of favorable events. You know, if you want to see it in a statistical manner. So it would be like that. So that would be the probability of collision. Right? You know, when there is collision, we will talk about probabilities, and we will use this. Now the scattering the mobility because of the mu I is supposed to be mobility because of the impurity is present, right? The change in mobility because of impurity atoms. Make it impurities, right? So if we then here is mu I is to the power 3 by 2. Remember, it's different from that. Mu I temperature के directly proportional होगा. Temperature increase होगी in ionized impurity situation में. Then the mobility will also increase. It is because temperature increase करने से charge की velocity बहुत ज़्यादा तेज होगी और वो impurity ions के करीब से तेजी से गुजरेगा. जब when it moves very fast near an impurity, it will have smaller chance of collision because it passes little time with the impurity. बहुत तेजी से गुजर जाता है. So it is like uh, understandable, right? Similarly, we will say mu I, the impurity, right? The impurity mobility, the mobility because of impurity atoms, will be inversely proportional to the concentration of impurities. Impurities ज़्यादा होंगे तो mobility कम होगी, क्योंकि ज़्यादा impurities हैं तो चार्ज को पास होने के लिए कई ज़्यादा चीजें हैं, उनमें से गुजर के जो है वो करंट प्रोड्यूस करेगा. So that is inversely proportional. Impurity concentration. If Ni is the impurity concentration, then it is inversely. We can combine the two. So mu I will be proportional to T to the power 3 by 2 and Ni. So we have now two proportionalities, right? Mobility because of impurity will follow this equation. Because of impurities, the change in mobility that occurs should follow this equation. And because of like thermal vibrations present, because of phonons, collision with phonons, then the mobility should follow this relationship, right? So the probability here, right? There was a probability here in the case of vibration. Okay, what is the probability here? The probability of collision, we will say again, because mobility is because of collision, effect is because of collision. So we will say, what is the probability of collision? Again, here in this situation. So the probability of collision here, right? We will say Pi, the Pi, right? That will be dT and divided by, there was pi, and that was tau I. The mean collision time, when there are impurities. ये small time जो है आप मुझसे मांग रहे हैं, मुझे बताएं इस टाइम में कितनी collision होगी. ये आपका वो है favorable event है और total event, right? So one is this thing, the probability of collision here due to only lattice vibrations or the presence of phonons or collision with phonons, and here collision with impurity atoms. So what is kind of the total probability? हम collision के मुताबिक बात कर रहे हैं, mobility collision से बनी है, right? Collision से मुताबिक. So what is the total collision, not the total probability of collision? So that will be as equation number 1 and equation number 3, right? total probability, right? That would be dt divided by tau is equal to this thing, dt divided by tau n plus dt divided by tau I. And the probability here, the probabilities are added here because these situations are independent. राइट इम्प्योरिटीज और फोनॉन्स हमने इनको सेपरेट किया हुआ है इम्प्योरिटी कितनी है इसका फोनॉन के साथ कोई ताल्लुक नहीं राइट फोनॉन्स कितने हैं इसका इम्प्योरिटी से कुछ the two parameters are independent therefore their probabilities are added right they are not multiplied so that will be the total probability. Now we put overlap 1 over tau is equal to 1 over tau L plus 1 over tau I. Right? Now we put the values of tau here. Tau was equal to mu and C star divided by E. That was tau from previous equations. So we put this thing here. So what we get is right 1 over mu is equal to 1 over mu L plus 1 over mu I. So the total mobility right, because of the different mechanisms. Like that, there is kind of capacitors in are resistors in parallel. Resistors in parallel. Kind of. So the total will be because of this one over this, one over this. So the resultant, what we get from this equation, that the resultant will be the smallest, will be smaller than the smallest of the two. You know, when we just evaluate this equation, what we get here, that the result mobility must be smaller than the smallest of the two, right? So that is the equation for mobility. Now we want to find, we want to know another important property in the discussion of transport, charge carrier transport. That is conductivity. Conductivity also and pocket phenomena. Right? And charge transport we call conductivity. Okay, there was some problem. So, what is conductivity, right? We want to know what is conductivity. So, we know that the current density is proportional to, what is the definition of conductivity? That is like Ohm's law. From Ohm's law, we know that J is equal to sigma E. We know that J is directly proportional to the electric field, right? That is Ohm's law. Our J is equal to sigma E, right? Where sigma we call conductivity of a material, right? Okay. So we also know that J was equal to E, right, from just our previous discussion, and mu and plus P, mu P and to E. Right? And that is equation number 1, and that is equation number 2. If we compare these two equations, right, we get that the conductivity is equal to E and mu and plus P and to mu P. Conductivity in semiconductors. So you can calculate the conductivity of a material by this equation. Sigma is equal to the charge of the electron, the concentration of electrons, mu the mobility of electrons. If you know these things, you know what is the conductivity of the material, right? And similarly, resistivity. Resistivity, you know that resistivity is the inverse of conductivity. Our conductivity is the inverse of resistivity. So resistivity rho is equal to 1 with conductivity, and that would be equal to E and to resistance. Right? So let's see what is the situation if semiconductors follow Ohm's law. Right? So let us check whether it follows or not. So we have suppose a Ohm's law and semiconductors. Yeah? Ohm's law in semiconductors. So suppose we have a slab of a semiconductor sample, and suppose L is the length, right? A is the area, and suppose we have applied a potential difference to it, right? Okay, so because of this potential difference or because of the field, there will be a current, and we define the current density. We define the current density is equal to current per unit area perpendicular. Similarly, we know that the electric field is equal to right V by L. We said electric field is equal to gradient of potential. Gradient of potential is dV by dx or dV by dr. So that is the potential difference is V and the distance is L. So that is the electric field, right? So if we put this in the definition of the conductivity by putting these two in equation number 1. In equation 1, right? So when we put this in equation 1, J is equal to, so I by A is equal to sigma, and E is V by L, right? Or V is equal to, from here, V is equal to L I divided by sigma into A, right? L1 over sigma is equal to rho, so we write here rho, right? And to L divided by A into I. Right? This thing is called resistance. This is the definition of resistance. Resistivity is equal to uh, the resistance, right? Proportional to that, inversely proportional to that. So it is equal to R into I, right? No. R, right? Resistivity is the resistance of, right, of a conductor of length L and cross-sectional area A. So here R will be equal to rho. Sorry, it is inversely proportional to, not directly. Anyway, the voltage is equal to then the go to mine. So it is like resistivity proportional to F. That is R. Right? The resistance is proportional to length, directly proportional. Resistance is inversely proportional to the area. Where resistivity is constant of the constant of the material, right? It is a signature property of the material. The resistivity does not depend upon length. Resistivity does not depend upon area. Resistivity does not depend upon any dimension of the material. It is a constant of the material. So, what we get from here is yes, semiconductors follow Ohm's law. General semiconductors follow Ohm's law. Right? We got it from here. So now, for a p-type semiconductor, right? What will be the situation for a p-type semiconductor? Conductivity for a p-type semiconductor, right? We know that sigma is equal to E, and here n mu n plus p into mu p, right? But for p-type semiconductor, right? This will be benchmark, will go to 0. So therefore, the conductivity can be written as E, P, and this is P, mu P. For a p-type material, right? Similarly, for so conductivity and the current density, right? Jp for the p-type material can be written as E mu P into P. Just playing with this. This is what we could have done already. The previous equation, the current density equation. You neglect this. Similarly, if you want the current density because of electrons, you neglect this thing. And that is nearly equal to the other term. Right? We are getting late. There is another important discussion, but let us do it in our next lecture. So how many people are present?
सर जी
Any
अस्सलाम वालेकुम
questions?
शेर नबी में
Walaikum salam. Uh-huh.
नो क्वेश्चन सर जी शेर नबी में
जी
मख
जी.
नेट कार न को
हाँ.
زي
सब
استرمك
वक्त है.
शेर مخ نو ما من नेट कार न को शेर
हाँ.
नबी में
देखते हैं कार ना कहूँ.